Thank you very much. The area of probabilistic combinatorics or combinatorial probability, whichever way you want it, I shall be talking about today, has been very active in the past decade or so. Nevertheless, it's very much the younger brother of various other closely related fields like percolation theory and the theory of random graphs. Actually, there are strong Brazilian connections. Some of the earliest results are due to Roberto Schoenmann, and Robert Morris, our chairman today, has been proving some of the very best recent results. Okay, I shall assume that you know nothing about bootstrap percolation. The name reminds you, of course, of percolation, but in fact it has very little to do with percolation. The main thrust of the topic is what happens after you have started with some random sites. And unlike in percolation, where that's the end of the story, you select your random sites and you look at the picture and then you say, it goes this way or that way. I mean, here a deterministic process starts, and we are interested in what happens at the end of this process. Okay, so if all goes well, I shall say a few words about these topics, and if it doesn't, it's absolutely fine. I shall prove essentially nothing, really. I mean, strictly speaking, I shall prove nothing. I shall doodle occasionally, and I shall challenge you to do one or two beautiful problems that you could call puzzles, but anyhow, we'll see them when we get to them. Okay, so what's a cellular automaton? Most of you are bound to know that this area was started by Johnny von Neumann, who, after a suggestion of Ulam, introduced these automata, which were, the hope was that they'll be self-reproducing, and they actually eventually constructed such a device. The main thing is that we have some sides, vertices, edges, whatever, in various positions, usually finitely many positions, or just 2, 0, and 1. Every object has just two states. It's in state 0 or state 1. And then, having decided what our initial configuration is, some local update rule tells us what to do next, and next, and next. Okay, the most famous, certainly the most popular cellular automaton is Conway's Game of Life, which he worked on with his groupies in the early 70s in the common room of the old Maths department in Cambridge, and they were very happy to find out various little objects which fly this way and that way. Anyhow, I'm sure if you look on the web, you'll see tens of thousands of pages devoted to the Game of Life. But that's not our topic for today. So, just a reminder that actually, strictly speaking, it wasn't von Neumann who introduced it. There were earlier attempts at modeling the brain, and that was already a cellular automaton. Okay, now let's turn to our main topic, an extraordinarily simple cellular automaton, which we'll call bootstrap percolation. So that was introduced over 30 years ago, again for reasons to do with physics. So let's define our bootstrap percolation, as it says on the slide. So you start with a graph, the whole process, let's say, takes place on a graph, to be precise, on the vertices or sides of the graph. At the very beginning, some of these sides, vertices, are infected, and everything else is susceptible. And as time goes by, every vertex which has at least R infected neighbors itself becomes infected. And then in the next time step, the newly infected sites may infect other sites, and so on. Eventually, of course, the process stops if we take a finite graph, although we may take an infinite, as we shall a little later. And then we get the closure of the original set. It's a set containing the original set, which does not infect any more vertices. Okay, of course, it's supposed to model a spread of infection, just as percolation was supposed to model the way a liquid goes through a porous medium. Okay, maybe the most basic thing is bootstrap percolation on grids of various dimension, and that's exactly what we shall take. In the simplest case, we have an n-by-n chessboard, but the chessboard is not colored black and white as a decent chessboard is, but some of the squares, some of the cells are red, and the others are white. The red ones are the ones we think of are infected, and they infect the white ones by the rule that if a cell has two infected neighbors, it itself becomes infected in the next round, and it continues. So here is an example. If that's our initial configuration, then you may concentrate on any one of the cells and see what happens in the next round. If it has two red neighbors, it should be red. Of course, probably I made a mistake, but still. So let's say this is in the next round, and then certainly the little cell in the white cell in the bottom center should get red. It even has three neighbors. It should get dark red, and so on. And with this setup, I jumped. Everything will be infected eventually. Okay, if that happens, then we say that the initial configuration percolated. And the main question is, what can we say about percolating configurations? Okay, first let me say a few words about extremal problems. This is not the main thrust of the research on bootstrap percolation, but it has lots of interesting and difficult problems. Okay, so let's consider exactly the percolation I mentioned a minute ago, n-by-n board, two neighbor. Okay, at least how many cells do you need at the beginning to infect everything at the end? Now, of course, it's easy to see that n of them will do. Indeed, you can take... What's happening here? Pardon? It's on strike. So if you start with with an infected diagonal, let me try it again. If you start with an infected diagonal like this, then in the next round, the two neighboring diagonals will be infected, and so on. So certainly in n-1 steps, everything will be infected. Okay, so far so good. Utter triviality. But then the question is, that's not where I was. The question is, can the same happen if you have only n-1 infected cells? And this is the first little puzzle or problem I'm telling you. Do think about it. I can assure you, if I had mentioned this problem to Israel Moiseyevich Gelfand or Paul Dirac or J. Littlewood, there is no way they could have refused to think about it. Inconceivable. And of course, Erdős would have been very nervous until he found the solution, because it should be immediate, and maybe it's not as immediate. Actually, what is an obstruction? What obvious obstruction do you see of two-neighbor percolation on the square grid? Of course, I think the most obvious obstruction is the existence of two neighboring empty columns or rows. Just imagine that all these are healthy, not one of them is infected. In that case, of course, there is no way the infection can break through either way. Even if everything here on the left is infected, everything on the right is infected, yeah, so far so good. That this set is closed, the infection doesn't go any further. So one's first idea is that, okay, we are looking for two neighboring columns which are empty or two neighboring rows which are empty. And if you take that into account, then of course you conclude happily that you need at least n over 2. But that's not what we want. We want n. And I won't tell you anything more about it except a very strong hint, which maybe one shouldn't give, that the solution is extraordinarily simple. Of course, that can cut both ways. It can be a strong hint to some people, and some other people are very annoyed that if it's so trivial as you say, why don't I see it in 5 seconds, as I should? It depends on, again, what happened. But now it's red. Am I going the right way? No. Okay, now at last, it seems it's difficult to get out of a figure. Okay, so now let's take a very similar thing. Let's take the n-dimensional hypercube, so 2 to the n sides, and with the obvious connections. Exactly same question. Suppose we take two neighbor percolation on the cube, on the hypercube. How many infected sides do you need to get it? Is maybe a little less trivial than the other one, but you should certainly not sleep until you have actually done it. If you sleep, something is wrong. No, you must do these two questions before you have your first beer, or after the 5th beer. Okay, and that you can do tomorrow. Okay, now what about the time? For the percolation, if you start with the diagonal, in n-1 steps, in time n-1, you finish everything. Okay, is at least how many do you need? Maybe that many. But what about at most? And that is actually quite a bit tougher. And there are several variants, but two variants is what happens if you use the minimal number, which let's assume we have shown is n, or what happens if you take any number of infected sites. So how slow a process can you give? Remember, the diagonal infected everything in n-1 steps. Okay? Now, take any configuration you like, which should percolate, should infect everything, but should do it slowly. It cannot do it fast. I mean, of course, the speed is given. There's nothing you can do about it. It would be silly to ask you what you think the answer is, or about what the answer is, but the answer ought to be a bit surprising. I'm so sorry, there is another Brazilian connection, Fabrício Benavides. How could I forget him? Of course, that's not by chance that we have this transparency. So the longest time it takes is 5n² over 8, which is ridiculously slow. Remember, if you infect every cell one by one, starting from, then you need n². So it really, I mean, had you thought about it, you would find the result surprising. And the second is similar, but I think even a little bit tougher. And here the answer is 13n² over 18. Okay, and here is a slow infection process, provided we can start it. So now it goes 1, 2 rows. 1 row, 2 rows. 1 row, 2 rows. So the main part of the process, whatever we may call the main part, it looks like it does it in 2/3 of the time. Yes, but at the beginning, now, again, the question is how to manipulate these things. But at the beginning, the process will spend a fair amount of time doing it even more expensively. Watch it at the beginning. It goes really one by one. So that adds to the 2/3 quite a bit. Okay, and this is a genuine theorem, very far from trivial. Okay, I know I can't stop it. And even now it's a problem how to go to the next page. Okay. And there are, quickly there are other problems as well. Of course, you may take a percolating set which percolates itself, but no subset of it does. At most, how large can that be? So, can it be really large? And this is an early result of Robert Morris, in spite of his publication date, that on the n by n square you need somewhere between these two bounds. And there has been a recent follow-up of that result by Riedel first of all, on the cube. Surprisingly, on the hypercube, he could determine the exact value, which is about 2 to the d over 4. And it is surprising that he could do bang the exact value. And as a corollary of the method, for grids, he gets a bound of this kind. Okay, but that's the part which is fun to do, and there are lots of questions here which would be extremely useful for the random case. But the main thrust of the theory, it concerns random choices. So let's turn to this one. Now we start with a random infection, the simplest kind. Choose some probability p. Infect every site independently of everything else with the same probability. And you get a random configuration at the beginning. Does it percolate or it doesn't? And life tells us, and everything we know about maths and probability tells us there is a critical probability about which there is a phase transition. Below that, it doesn't, unlikely to percolate. A little bit, if you take the probability a little bit bigger, it's very likely to percolate. So this is the kind of thing we are interested in. What is the critical probability at which percolation becomes likely, and is this transition really sharp? Is this really fast? Does it happen really quickly that you hardly change p and the percolation goes, and the probability goes from tiny to huge? Okay, and first, what happens, when the whole area started, then somewhat surprisingly, apparently it was a problem whether there is a critical probability in the plane or in the cubic lattice, in z to the d. Just as in percolation, there is a critical probability, and the very first theorem, or the theorem we proved before we proved the very first theorem, is that there is a critical probability which is non-trivial, which is not 0, not 1. So at the very beginning, it was a possibility that something similar happens in the plane. Not really, and then Van Enter and Schoenman proved this result, that if you take it on the d-dimensional cube, if you take R neighbor percolation on the d-dimensional cube, then for R at most d, the critical probability is 0, and R at least d, so R greater than d, the critical probability is 1. Okay, I mean that's essentially instant, but still, so that I doodle a little bit, let's see why the result is obvious. So, for example, if P is strictly positive, then what we would like, let's just take the plane that our random selection percolates with probability 1, almost surely. Okay, let's do our selection in 2 rounds. Let's do this sprinkling, which is often useful in probabilistic combinatorics. So first we select sites with probability P over 2, and then again with P over 2. Altogether we select it with little less than P over 2, but who cares? In fact, it's good for us. It's legal. Okay, so after the first selection, it doesn't matter what you demand, you will find it somewhere in the plane. If you want, may I have a million by million square all infected, of course you have it somewhere. May not be in this galaxy, but somewhere you will certainly have it. Okay, so we have it. Let's focus our attention on this big square. Okay, now what happens in the next round? Again, we infect sites at random. So here we have our huge square, and the question we ask, what is the probability that we go out to an n by 2, let's say we are very modest, n plus 2 by n plus 2 square, so just add to it one more column here, one more there, one row, one row. That's all. And we do it in the most primitive way. Suppose any one of these cells here is sitting on the side, is infected. Oh, that's brilliant. Once this is infected, the next one is infected, and the next one is infected, and that one, and similarly here. So the whole side will be infected. Correct? Okay, and now if any one of these cells sitting here is infected, the percolation spreads to that one. And then if any one of these, so it's a bit thick, is infected, then the percolation spreads to that one. And if any one of those n plus 2 sites is infected, we have done it. Okay, so what's the probability of that it does not happen? How can it not happen? We mustn't have any of these infected. In one of the 4 cases, so either none of these n sites is infected, or none of these n sites is infected, or none of these n. I mean, certainly compulsory. Okay, what's the probability? Tiny. If n goes to infinity, then the whole lot, of course, goes to 0. So the probability of failing is as small as you like, provided you choose or your initial square large enough. Oh my God. Okay, now, so that's not the issue. The issue is always finite. Infinite is easy in bootstrap percolation. Finite is that we care about. So here is a distribution. Can you see at all? There are lots of, this is a somewhat big square, like 500 by 500, and there are some infected cells in it. These are the red ones. And now if we start the process, and it will all be yellow, that's how the infection spreads, and we get everything. So the question is, what P is likely to produce this? Okay, so we are interested in this critical probability. Let's define it essentially as the probability at which the likelihood of percolation is 1/2. Okay, it doesn't tell us that there is anything critical about it, but the results will always say that if the probability is little less than this PC, at which the percolation probability is 1/2, then we are very unlikely to percolate. If it's little bigger, we are very likely to percolate. So there is this phase transition occurs at that stage, taking it in the crudest sense, that if you take the ratio going to 0 or 1, it certainly works. Anyhow, we have this phase transition, and what we care about is this critical probability. So is it clear what I mean by critical probability? Yeah, there could be several definitions. Here I give just about the weakest, that if a probability is much smaller than PC, then it goes to... that's not what I mean in the second. It's better to go on. It's nonsense. The second bit was nonsense. Sorry. Okay, so now what about the two-dimensional grid, or any grid of fixed dimension? The starting point is this really basic result of Eisenman and Lebowitz, two wonderful mathematical physicists, who proved that the critical probability is about 1/log n. So they proved that if the probability is less than, let's say, 1/1000 log n, then the probability of percolation tends to 0, but if it's bigger than 1000 over log n, then it tends to 1. And a very elegant proof was given by Bolog and Petter. Okay, so it's a nice result, and certainly was a starting point, but it does give a pretty crude picture. On the other hand, looking at what went on, it didn't seem to be likely that anybody could actually make it really precise. So it was quite a surprise when Holroyd, Ender Holroyd, at the time in Cambridge and now at Microsoft, could actually determine the constant in this. So could prove that the critical probability is about a constant over log n, where the constant is pi squared over 18. And it's a wonderful result, and certainly took most people by surprise that it actually came out that nicely. And since then, not immediately, because it's a pretty tough nut to crack, much sharper results have been proved by Grafner, Holroyd, and Morris. The question is what happens. Can you pin it down better? And can you make the transition sharper? And can you find out what the next term is? And again, it's not the kind of thing one could guess. I haven't met anybody who could just guess it like that. That the next term is constant over log n cube, and it's with a minus. So the critical probability satisfies that. So it's a little bit smaller than pi squared over 18 log n, and the little bit is some constant over log n to the 3/2. And I'd be delighted if one of my students could determine little c. I'm 99% certain that he would get a fellowship in a Cambridge college. Okay, or in an Oxford college. Okay, now higher dimensions, again, Eisenman Lebowitz proved the rough bound, but for L equal to 2. And then it took quite a while for it to go to L at least 3. So if the infection parameter is at least 3, suddenly it's much tougher. The question is much tougher. And again, it was pretty good. The Cerf and Cirillo and the Cerf and Manzo actually determined the rough order of the critical probability. Now, why this big difference between 2 and 3? There's an immense difference. Why? There's an extremely good reason and very simple reason. Because for L equal to 2, we know what closed sets are like. We have an exact description of those sets which do not infect anything else. Namely, they are unions of bricks which are not very close to each other. Unions of bricks, so rectangular parallel pipettes, which are not near to each other in the sense that there is no site within distance 1 of 2 of these bricks. If that happens, of course, you know that nothing can be infected, because a brick in itself, a square in itself, if it's sitting in the sea, cannot infect anything else. I mean, this one has only one neighbor, and all the cells on the sides have just one infected neighbor. Everything else has no infected neighbor. So the infection stops here. Okay, so to continue the infection, you do need 2, and that's exactly what happens. And that also gives a very nice description of the whole infection process. What is going on? Suppose at some stage you have got a bunch of bricks, and so the whole set, the infected set, is that. In that case, what can you do? If you can find 2 bricks which have a neighbor, which have a common neighbor, then that's wonderful. Then this will get infected, and all this thing is filled. That is filled, and you can replace the 2 infected bricks by the union, by the smallest brick containing the union. Similarly, if it's like that, of course, then this gets infected and so on, and you replace it like that. Or if this is the setup, so there is an infected, the distance, there is one cell which is within distance 1 of 2, then these 2 are filled, and then the whole lot is replaced. So the infection goes in an extremely simple way. You have got your infected bricks, and when you find 2 which are near, then you replace them by the smallest brick containing both of them. Okay. And the trouble is that for L at least 3, there is nothing like that known. Not clear that there is nothing like that, although I strongly suspect that there is nothing which is remotely simple, which is remotely usable to get bounds on various probabilities. So one has to use various substitutes. One has to approximate the possibility that percolation can happen, and then and use that to get bounds on the critical probability. Okay, I promised a little more doodle. So why? For example, what about this Eisenman-Lebowitz result? Why is at least one part extremely simple from what we have just said about this process, the speeded up brick process? Now, how does the process go? You look for 2 bricks, and if they are near, you replace them by the union. What happens to the perimeter length? The perimeter length of the union is at most the sum of the perimeter length. It doesn't matter which way it is, it's always the case. So if you take, for example, the maximal perimeter length as it grows, as the process continues, what do you see? That it at most doubles. It cannot do more than it grows, but at most doubles. Okay, so if at most doubles, then no matter what bounds you say, let me stop when there is a perimeter length between 1 million and 2 million, you can have it. At some stage, you will have a brick of perimeter length between 1 million and 2 million, which arises in the process. Now, if it arises in the process, then suppose here is the brick in question. What can you say about it? Of course, how was this infected? Oh, by uniting little bricks inside. And how was that infected? The same way. In particular, this was infected using only infected cells inside. Same thing here. So how was the whole lot infected? It was infected on the basis of the infected cells you can find in the rectangle. We are talking about rectangles, in the rectangle itself. Is it clear? So whatever bound you say, okay, like L and 2L for perimeter length, you will find a brick of perimeter length K, which is infected by cells at the beginning, by the infected cells it contained at the very beginning. It's, as one would say, or one says, internally spanned. Okay. So what I see, I changed the letters. I wanted this to be L. So, for example, you can have it like that, whatever. And then what you know is that somewhere in the process there is a rectangle of perimeter length, as I say here, 4L, which is infected by the cells it contains inside. Okay, how many cells do you need? According to our little puzzle, let's say that you have shown that if the perimeter length is 4L, then you need at least L cells, infected cells at the beginning. The area is at most L squared. You have got a few ways of depositing it, something like constant n squared log n squared, and so on. So the whole probability that you can infect such a rectangle somewhere is no more than the left-hand side, which is no more than the right-hand side. And if Pn is small, that's way overkill, then the right-hand side tends to 0, so the probability of percolation tends to 0. In particular, the critical probability is at least 1 over, it's 1,000. I'm sorry, I can't count zeros. I think at some stage I added a 0 on the left, just to be on the safe side. Yeah, okay, so that actually proves one of the bounds in Eisenman-Leibowitz, whose importance is not the difficulty of the proof, but the fact that they drew attention to this phenomenon. Okay, now to get constants in 2 dimension was non-trivial, but to get it in the higher dimension is considerably worse. And after several other results, all needing 50 pages to prove, we have got this recent result which tells us that for every dimension D and every R fixed, the critical probability of percolation in R neighbor bootstrap percolation on the n to the D grid, now D is fixed and n goes to infinity, is about this constant over log iterated R minus 1 times raised to D minus R plus 1. Okay, and not only that there is a constant, but we could determine the actual constant, just which was actually conjectured by 3 of us a little earlier. And how is the constant determined? What is the constant? I'm just flashing it on the screen to say that it's not that the constant is 2, which is sort of all right, or E, but it's given by this process, or defined beta ku as this function, and then use that to define gk, and then take this integral, and that is lambda, which is our required constant. is not what would spring to your mind after 2 minutes. And in some sense it was a miracle that in Holroyd's case, this constant, because of course this is exactly, you plug in the right D and R, you get Holroyd's constant. It was a bit of a miracle that the integral could be actually worked out explicitly. Okay, that was if we fix the dimension and let the side length go to infinity. What happens if we fix the side length and let the dimension go to infinity? Then the starting result corresponding to some extent the Eisenman-Lebowitz was this result, but which also shows there is less of a nice function than in the grid case. And recently, not so recently, we proved much sharper results. We actually determined the actual constant, which is again not something incredibly easy, but not as nasty as in the other case. Okay, there are lots and lots of results, but I mean, all you would see is that, okay, it can be done and it's probably nasty, and I definitely don't want to go into any kind of maths because it's not nice to torture you. But rather, let me finish by saying a few words about a topic that has been studied only recently. In some sense, it was studied quite a while ago, but properly only recently. So this is graph bootstrap percolation. There are lots of variants. The one I'm saying that fix two graphs, G and H, or if you like, really fix H and take a graph G or a graph sequence. G could be like a sequence. So let's define H bootstrap percolation on the vertices of G as follows. As I write up there. So think of G as the board, replacing the n by n grid or n to the d grid, or whatever lattice you have in mind. So it's just a graph, and the infection goes by infecting a site, a vertex, provided it is the last healthy vertex of an H subgraph. So if somewhere you find an H subgraph whose vertex in which that is the last healthy vertex, and then you infect it, and that in the next round, and it continues. And of course, there are analogous processes. Ridiculously, I introduced it, but only in the extremal case quite a while ago, and much research was done on that. But in the proper bootstrap percolation sense, we have been working with only rather recently with Rob and Yuji and Oliver Reardon from Oxford. Okay, so let me give a very, very special case, just about the simplest you can think of. Everything is a complete graph. What can be easier than a complete graph? So our board G is a complete graph, and our graph, the infection, is going along a small complete graph. But now we play the games, this particular game, on the edge set. So you have a complete graph. Some of the edges are infected, and then whenever you find let's say H is a C4, is a 4 cycle, whenever you find an edge which completes a 4 cycle, so the other 3 edges are infected, then you infect it. You put this in. And then again, where is one? For example, 1, 2, 3, you infect this one, because together with these 2, it forms a 4 cycle, and so on. But now let's take the absolute simplest case when you infect complete graphs, like K4. So what would you infect? You would infect an edge if the other edges of this complete graph on 4 vertices have already been infected. Okay, that's the process. And now select edges with probability P as always, or if you like, you take the classical binomial random graph G and P, usually called Erdős-Rényi graph. And the question is, if you start with that graph and you complete, put in an edge whenever it completes a K4, and you keep repeating it, for what P is it likely that you end up with a complete graph, that everything will be infected? Okay, of course, where should we start? With the complete graph being the triangle, and that is totally trivial. Why, what happens if your percolation process is that put in an edge if it completes a triangle? Of course, if your original graph is not connected, there is no way you can complete it, because there is no way you will infect an edge joining a component to another component, because it should be sitting in a triangle. So it cannot be done. So a necessary condition is that the original graph is connected. Yeah, but if it's connected, then we are done. K3 percolation happens. Indeed, if your original graph is connected, so there is a spanning tree in it, in that case, in the first round, any 2 vertices at distance 2 in the tree will be connected, and so on. And so on. The process instantly finishes. So what is the critical probability? It's nothing but the critical probability of connectedness, which is log n over n in the pretty sharp sense that if omega n is any function tending to infinity, we get connectedness. Tending to minus infinity, we get disconnectedness, and in between, both can happen. Okay, so the case K r equal to 3 is trivial, given this 40-year-old Erdős-Rényi result, which in itself is pretty easy. But what about other cases? What about K4? And we proved that for K4 the critical probability is about square root 1 over n log n. But we don't know that there is a constant. Of course, we cannot even prove that there is an actual constant which will be the critical probability. But we have these bounds, in the sense that if the probability is at most the left-hand side, the probability of percolation tends to 0. If it's at least as large as the right-hand side, it tends to 1. That's what this formula is supposed to mean. Okay, what about Kr? What about larger values of R? Again, we have bounds, but the bounds are even weaker depending on R. Let's define this constant lambda R, which is about R over 2 for large R, and the critical probability then is given or satisfies these two inequalities, which are not that close to each other, so we are off at least by a factor of log n. And we all know that to get rid of that factor is 99.99% of the work, usually, not necessarily. Okay, so I think that's about all I was hoping to show you. I should like to emphasize that, of course, there are lots and lots of open questions, and the whole area is very, very much at the beginning. Just as in percolation, one would love to know what happens at the critical probability. So one would like to prove conformal invariance of whatever happens at the critical probability. Similarly here, one would love to see what happens when our probability is exactly the critical probability. What kind of configurations you get at the end, which are the closed setup, closed configurations you end up with. But much closer to home, it would be great to determine the actual critical probability, at least the order of that for this very, very simple case, which really is the simplest imaginable case, and ideally determine the constant. And in that case, determining the constant, even the case r equal to 4 is of interest, because certainly we couldn't do it. Thank you very much.